Welcome to this screencast about redox. Remember, chemical reactions are all about electrons being lost, gained, or shared. Losing or gaining electrons is redox. So losing electrons is oxidation, LEO for Leo. This means that the charge goes up because you're subtracting negative electrons. Most of the time you see the charge go from 0 to positive. Sometimes you can see the charge go from negative to 0. In both cases, though, the charge is going up. Gaining electrons is reduction. This means that the charge goes down, which is reduction, going down. Usually this means going from 0 charge to negative charge, but sometimes it could mean going from a positive charge to 0. I'm going to talk about 4 ways that you can either use singly or sort of in combination to analyze a reaction and first off determine if it's redox and then determine what is being reduced, what is being oxidized, and what is remaining unchanged. I'm going to use 3 different sort of chemical ways to think about it and also talk about how a biologist views redox. We're going to be talking about 4 different examples. Pause the video and try to classify these reactions. Okay, number 1 is a synthesis reaction. Number 2 is a single replacement reaction. Number 3 is a double replacement. And number 4 definitely looks like combustion. Notice that we've got oxygen, carbon dioxide, and water. We'll talk more about all of these in a little bit greater detail as we get to them. All right, our first example is the synthesis of iron oxide from iron and oxygen. One way that we've done this in class is burning still wool. Okay, let's think about oxidation numbers. So one of the rules for determining oxidation numbers is that if you have a pure element, the oxidation number is 0. Both iron and oxygen in this example are pure elements. Even though we see a subscript, there's only one element here with oxygen, so it's got a 0 oxidation state. This is a compound with a metal and a non-metal, which tells us it's ionic, which tells us that electrons have been lost and gained. The metal is always positive, the non-metal is always negative. We can pretty much guess that this oxygen is going to be 2-, so we have 3 times a 2- charge for a -6 total charge. And we have, that means the 2 irons here must be 6+, and there's 2 of them, so we can figure that there's 2 times 3+ to balance this compound out. So iron has gone from 0 to 3+. Oxygen has gone from 0 to 2-. Oxygen has been reduced. Its charge has gone down, and it has gained electrons. The iron has been oxidized. Its charge has gone up. Here's another example of a reaction we've done in class. This is the single replacement of iron for copper in copper sulfate. We saw blue copper sulfate solution. I dropped a nail in it, just like you see here. And after a few days, we saw that the blue solution turned to a sort of greeny tan color as the copper sulfate was being turned into iron sulfate, and the copper in solution was turned into pure copper as the iron dissolved out of the nail. So we can think about oxidation numbers, but here's a case where we don't really need to get super caught up with them. This is a single replacement reaction, and you'll notice that on both sides we have the same polyatomic ion, sulfate. Sulfate, in this case, is 2- on both sides, and that means it's considered a spectator in this reaction. It's not changing. And that's typical of these polyatomic ions in a lot of reactions, especially these single replacement reactions. It's the same thing, it's not actually being changed. So now we can focus on the iron and the copper. We could worry about charges, but we don't even really need to. We see that this is an ionic compound. That means that the metal is positive and the second part, the sulfate, is negative. So we can see that the iron is going from a 0 charge, because it's a pure element, to positive. The copper has gone from positive to 0, because on the reactant side, it's a pure element. So that means copper has been reduced in this reaction, and iron has been oxidized. So we didn't really have to think too hard about oxidation numbers. We didn't have to do any sort of calculations with the sulfur and the oxygen just to get this figured out. We could, if we wanted, figure out that the copper here and the iron here are both must be 2+, since the sulfate is 2-, but that ultimately isn't super necessary for this one. Okay, here's another reaction. If you look closely at this, you'll see that this is double replacement. It's easiest to see this if you think about the water actually being HOH. So we've got the hydrogen swapping places with the sodium and joining up with oxygen and hydrogen, and then we've got the sodium swapping places with the hydrogen and becoming sodium chloride. So this is definitely a double replacement reaction. You could also look at this and see it's a molecule that starts with H. This tells us that we have an acid. This is hydrochloric acid. The other reactant ends in OH. That makes this a hydroxide. Well, it makes it a hydroxide because there's a metal here, which tells us that we have an ionic compound that ends with a hydroxide. So this is a base. Specifically, it's sodium hydroxide. Here we have water, and sodium chloride is obviously a salt. So we have a double replacement and an acid-base neutralization. So both of these tell us that this is not redox. Now you could get deeper into the analysis and think about why this is. For example, the hydrogen on the reactant side has an oxidation number of +1. Over here in water, it's also +1. The chloride is 1-. Over here, it's still 1-. The sodium is 1+. Here, it's still 1+. The oxygen and hydrogen in the hydroxide are both 2- and 1+. And so multiple ways you can figure out that this is not a redox reaction. Here's our next reaction. Pause the video and take a close look at it. See why you might think that it's a combustion reaction. Okay, this is a very classic reaction. This is the reaction, the balance formula for something called cellular respiration. This is the chemical reaction behind a pretty complicated process that our bodies use to convert food energy into usable energy for our cells. So here is how it typically is, you can think of it, is sugar plus oxygen, the oxygen that we have to breathe to live, is combined together and creates carbon dioxide as a waste product. This is what we breathe out, plus water as sort of another waste product that just gets added to the water in our bodies, plus energy. It does look like combustion, the reaction, and you actually can combust sugar with oxygen by literally setting on a fire. You see this when you roast marshmallows. So we have an organic compound plus oxygen creating CO2 and water and releasing energy. So any sort of fire is oxidation, and this reaction looks like combustion. It's oxidation happening, but it can also happen in without releasing so much energy that we catch on fire, and it's how we get energy from our food. So we could break down all of the oxidation numbers on this. I've put a link in the presentation if you want to get deeper into how all of this would work with a Khan Academy video, but just briefly, oxygen here has an oxidation number of 0. In both of these, CO2 and water, it's got -2. So oxygen has been reduced. The carbon here, if you work out the oxidation states, the carbon has a charge of 0. This is because the hydrogens and oxygens are going to cancel each other out. So that means this whole thing being a neutral covalent compound, that carbon is going from 0, 4+ on the product side. How did I get 4+? Well, I have 2 times 2 minus for the oxygen, the CO2, which is 4-, so the carbons must be 4+ oxidation states. So carbon is going from 0 to 4+, so it's been oxidized. In a certain way, you could say that hydrogen is a spectator. Again, see the video for more details on this. But from a biologist point of view, the way a biologist thinks about oxidation is hydrogen reduces, oxygen oxidizes. So from a biologist's point of view, you look at this, you see that carbon has gone from being in a compound to being by itself with oxygen, so carbon has been oxidized. You can also see that hydrogen in this compound has been added just to hydrogen in the product, so hydrogen has also been reduced in this way of thinking. This differs from looking at the oxidation numbers. Don't get too fussed about that. What has hydrogen been added to? Well, the hydrogen has been added to the oxygen to make water, and so that means that the oxygen has been reduced in this process. Takeaways, go back and review the slides in the presentation to see that they're true, and I'll be following this up with some more lessons. Thanks a lot.